All right, and welcome back to Data Structures and Algorithms. This time we're on chapter 4 out of 4, finishing our first week, and I assume that you finished Big O, so finally let's cover the final topic, binary search, and what I'd like to call it is a better way. Linear search is extremely honest. It walks every item one by one. But what if our data has a structure we can exploit? Here's the story. Imagine a physical phone book, names in alphabetical order. You want to find Lopez. Do you start at Aronson with a double A and flip page by page from 1 to 100? Of course not. You'd be there all night. What you'd actually do is open the book near the middle, and you see the name Miller. Now, here's the key move. You know Lopez comes before Miller alphabetically. So, you throw away the entire back half of the book, and you never look at it again. Then, you open the middle of what's left and see Garcia. Now, Lopez is what's after Garcia. Throw away the front half, open the middle of what's left, and repeat. That trick, that's binary search. It works only because the names are sorted. If the phone book were in random order, that throwaway half trick is meaningless. Sorted is the requirement. So, here's the contrast. Let me say it once, and I want you to repeat it back to me. Linear search examines one item and then eliminates one. Binary search examines one item and it eliminates half. Say it with me. Pause the video to say it. Okay, and I hope you paused to say it. We're back. So, eliminating half with one comparison is the whole magic, and it's why binary search runs in O of log n. Now, which we know is amazing at scale. Before we look at code, let's play a little game so you can feel binary search in your own head. This game is called Guess My Number, and oops, it's a bit broken. But forgive me if I do get it wrong. I'm not a computer, so I may not provide the best way of looking at Guess My Number, okay? So this slide has an interactive game. The computer picks a number from 1 to 100. I guess it tells me higher or lower. I'm going to play it badly at first, then we'll pay attention to the contrast. I'm going to click new game so I get a new number that I'd have to randomly guess. I don't know the number at all. This is honest. You can download this from the Google files in the comments and then try it out for yourself. But mind you, if I fail a lot, but that's because I can't run this a billion times in 1 second. Unlike a computer, but let's proceed. We're gonna type 1, right? So it says 1 is higher, right? But let's do more. Higher. 4, 5, 6. Seems like the number is between 7 and 100. Huh. Since the computer keeps saying higher and higher and higher, I'm gonna die before I find this number. And that's linear search. Honest, but extremely slow. Now, let's play a little bit smarter and do a new game and get a new number. Let's do 50 and press guess. It says lower, so it seems like our assigned number is between 1 and 49. That's interesting. This is between 1 and 49. Let's guess 25. Cut it in half once more. Guess. The number is between 1 and 24. Let's guess one more time. Higher this time. It's no longer lower. So it seems like it's up for something between 11 and 24. I'd say 15 is a safe number. I got it. 4 guesses so far and 15 was the number. And that's how fast you can find it using binary search tactics. So that's how we see it. If we look at the counter, we found it in 4 guesses. Linear would have taken up to 100. The math, log base 2 of 100, is about 6.5. So we expect about 7 guesses for the worst case at most. Can anyone can anyone watching this video consistently beat 7 guesses for any number in 1 to 100? Or maybe beat my record, 4. Well, 4 is extremely lucky in what we'd call a best case scenario, but the answer is no. 7 is the theoretical minimum. You literally cannot do better with comparison, only guessing. It's a beautiful result, right? So, that pattern starts at 50. Half, half, half. That's binary search. Same algorithm, just done in your head instead of an array. Now that we know how binary search feels like, let's spell out the algorithm precisely. Let's zoom it in a bit. There you go. Binary search uses 3 integer variables, 3 pointers. I want you to write these down. We'd have low, high, and mid if I had a whiteboard. So low, short for low, the left edge of the part of the array we're still considering starts at 0. High, short for high, the right edge starts at array.length minus 1, which is the last valid index. Mid, the index we're currently examining, we compute this each iteration. Now, here's the mental model. Low and high define the range we still care about. Everything outside of that range we've thrown away as we search. Low and high close in on each other until either we find the target or the range becomes empty. Essentially, divide and conquer, divide and conquer, divide and conquer until you get to the very specific number you're getting. Because with all of these halving, you're going to get the right answer eventually. So here's some pseudocode on the screen. While low is less than or equal to high, keep going as long as their range isn't empty. Mid equals low plus high over 2. Middle of the range. Then 3 branches. If array mid equals target, found return mid. If array mid is less than target, the target must be to the right of mid. So shrink from the left. That's low equal mid plus 1 over here. Else this condition isn't satisfied, meaning array mid, our mid, is greater than target. The target must be to the left. So shrink from the right. See what we're doing here? We're just shrinking from the left and right depending on an if and else statement. So quick. Why do we say low equal mid plus 1 and not just say low equals mid? Why are we doing this whole plus 1? So, 2 reasons. First, we already checked array mid and we know it's not the target. No point checking it again. Second, and this is the most dangerous one, if you just wrote low equal mid, the range might not even shrink. The loop could run forever. That's the #1 binary search bug, and you don't want that. But if you've answered that we already checked mid, we already know array mid isn't the target. Since we just compared, including it again would be pointless. Plus 1 moves past our mid, and that's what you want to do. We can't use low equal mid because we always want to move past our mid. So now, the C# version. The code has 2 more details that we do actually need to talk about. Here's the full C# code. Same structure as the pseudocode, but with 2 professional details that you'll never forget after today. So as you can see in each line, I'm going to slow down on each 3 gotchas. The detailed one over here is look at how mid is computed. Int mid equals low plus parentheses high minus low divided by 2. Why this form? Why not just low plus high inside parentheses divided by 2? Which any sane person would write. So, take a guess. When would those 2 formulas ever give different answers? Now, if you've answered that never, since they're the same, it's almost always true. But there's one corner case on massive arrays. More than 1 billion elements, low plus high can overflow. Int.max value. Adding 2 large positive ints can wrap around to a negative number, which would crash the binary search. The subtraction form avoids this. It's a real bug that hit Java's standard library for years before they noticed. So that's a bit of programming insight for you. Sorry. So, detail 2. The loop condition, as you can see over here, while low high, this over here. Notice the equal sign. Do you know what it is? That matters. When low equals high, The range has exactly one element left, and we still need to check it. If we wrote less than instead of less than or equal, as you can see over here, we'd miss that last candidate. Detail 3. Return -1 at the end. Same sentinel as linear search. When low passes high, the range is empty. The target isn't there. Now, most students won't care about the overflow thing for homework. The two details that's going to actually hurt you on homework are the +1 and -1 in the updates, and the less than or equal to in the while condition. Get those wrong and binary search either runs forever or it misses these elements. Now, code is dense, so let's see it run. We're gonna run another widget again, so it's the same interactive widget as before. But now for binary search. The screen is sorted 3, 7, 9, 14, 18, 22, 27. We're searching for 22, and I'm pressing step. Now, before I do that, predict. How many comparisons do you think this will take? Now, let's proceed. Okay, so we're going to be pressing step over here. Step 1, low is 0, high is 6, so mid is 3. Array 3 is 14, but the issue is 14 is less than 22. So the target value must be to the right, and low becomes 4. Now watch the screen again. The left half of the array just dimmed out. Over here, we threw it away, and we will never look at the indices 0, 1, 2, or 3 again. We're already at the second iteration. The cell at index 5 highlights, because it's been found. 22, right? So 2 comparisons. That's just 2. Linear search would have taken up to 6 on the same exact array. As the array gets bigger, the gap also explodes. Now, here's the counter pills that we have over here. Comparisons and range size, right? The range went from 7 elements to 3 elements to 1 element. Each step roughly halved it. So we can also run it a reset, and we can just automate this process so you can see how it looks like visually, where it just sets a low and high until it groups it down all the way to 22. So let's write that as a trace table like we did for linear search. Same technique, more columns this time. We have 3 variables to track now: low, high, mid. And let me walk you through it. So here's point 1 of the trace. Iteration 1, low is 0, high is 6, mid is, let me compute, 0 plus 6 minus 0, inside of these parentheses, so we calculate that first, divided by 2, which is 3, right? So array 3 is 14, as you can see. 0, 1, 2, 3, 14. Is 14 equal to 22? No. Is 14 less than 22? Yes. So the low equates to mid plus 1 equal 4. Now let's go to row 2. Iteration 2. Low is 4. High is 6. Mid is 4 plus 6 minus 4 divided by 2 equals 5. Therefore, array 5. 0, 1, 2, 3, 4, 5. 22. Is 22 equal to 22? Yes. Therefore, we return 5. 2 iterations. We're done. On a 7-element array, that's about O log base 2 of 7. About 2.8 iterations in the worst case. And we just experienced it. Now, watch out. You might get an integer division warning. In C#, dividing 2 integers truncates. 7 divided by 2 is 3, not 3.5. So when you compute mid by hand, never write 2.5 or 3.5. Round down always, alright? So here's a bit of quick mental math. On a homework problem, you have an array of 7 elements. What's the worst case number of binary search iterations before you give up? Now, if you said 3, right, log base 2 of 7 is about 2.8, and we always round up because you can't do half a comparison. 3 iterations guaranteed. So, time to prove the magic mathematically. Why this is so much faster than linear. So, why is binary search O of log n? It's not magic, it's just math. Let me derive it for you. Here's the math on the screen. So we start with n items. After step 1, half are left, right? That's n over 2. After step 2, half of those, n over 4. After step 3, n over 8. And after step k, n over 2 to the k. We stop when we only have one item is left. So we set n over 2 to the k equals 1 and solve for k. Now, move things around. N equals 2 to the k. Now take log base 2 of both sides. K equals log base 2 of n. That's it. That's the whole derivation. The number of halvings to reduce n to 1 is log base 2 of n. So binary search runs in O of log n. Beautiful, right? You don't need to memorize this derivation, but you do need to remember the intuition of it. Each step halves, so total steps is log n. Let's go to the right side of the screen this time. Look at the comparison table. Down the rows, we have 10 items, 100, 1,000, 1 million, 1 billion. Linear takes that many comparisons in the worst case. Binary takes about log n. At 1 billion items, linear takes 1 billion comparisons. Binary takes about 30. Alright? It's crazy, right? We went from 1 billion comparisons down to 30. So, let that sit with you. That's why binary search shows up almost everywhere. Dictionaries, databases, Git, the search bar on your phone. If binary search is so much faster, you might be thinking, oh, Joaquin, why don't we always use it? Well, 2 answers. First, binary search requires sorted data. Second, sorting itself takes O of n log n, which is more expensive than one linear scan. So binary search pays off only when you'll search the same sorted data many times. Sort once, search forever. That's the saying in this industry for this. And you now have 2 tools. Let's see when to use which. So we're moving up to the wrap-up phase of everything. This is the secret chapter 5 of all 4 of the chapters. So comparison table. Linear search on the left, binary search on the right. Same categories down the rows. Alright? So best case, both are O of 1. If you're lucky, both find the target in one comparison. Worst case, and this is the headline difference, linear is O of n, binary is O of log n. That's the gap. In the space, both are constant. Neither algorithm allocates extra storage proportional to input. Good, because recursive binary search uses more stack space. But we did the iterative version today, and I think Sir's gonna cover what recursion is eventually. Good luck with that. Alright, so data requirement. Linear works on anything. Binary must have sorted data, and that's the price of speed. We have code complexity 2, Linear is 4 lines. Binary is 15. Plus careful off by 1 logic. Binary is harder to write correctly than for linear. Now, best fit. Think of it this way. Linear is for small or unsorted arrays or single lookups. Binary is for large sorted arrays where you'll do many lookups. Alright. Now read this with me over here. Sorting first costs O of n log n, so binary search only pays off when you'll search the same data many times. Concretely, if you'll do 1 search, just linear scan. If you'll do 1,000 searches, sort first and use binary. Let me give you a decision tree so you can actually use it on homework. Here's the flowchart, 2 questions in this exact order. Memorize this order, it's gonna do you wonders in the future. Question 1, is the data sorted? Is the data sorted? If no, done. Use linear search, okay? If yes, proceed to question 2. Question 2, will you search many times? If no, opt for linear. It's simpler, right? Simpler and fine. If yes, use binary search. The pre-sort investment is always going to pay off. So that's it. 2 questions, always ask in that order. Sorted, many lookups, that's it. Now, here's the honest answer as well. An honest piece of engineering wisdom as somebody who does work in this industry, and this might surprise you. For small arrays, say under 50 elements, which I hope you do know what an element is, linear search is often faster in practice than binary. Simpler loop, better CPU caching, and less branching. Big O is just about scale. It's not about every situation when n is small, like the array of grades for one class. Just write the dumb thing. Linear is fine. Do not over-engineer, like as I said earlier. This is a mature engineering wisdom. In an interview, they'll expect binary search as the quote-unquote correct answer for sorted data. But in real industry code, you'll often see linear search on smaller arrays, and that's alright, that's fine, it's perfect. So that's it. Last slide. That's the whole class in 4 ideas. And here's a bit of take-homes from me is everything we did today. So yeah, it boils down to these 4 ideas on screen. If you remember nothing else, remember these. I'm going to read each one. Don't take notes, just listen, alright? So idea 1, arrays are numbered boxes. Contiguous memory, index from 0, constant time access, the foundation under everything else is here in this semester, right? Let's review all of these. There you go. There you go, okay. Idea number 2, Big O is a language for growth, right? So, shape, not seconds, as I said. Drop the constant, drop lower order terms, report worst case as guarantee. Idea 3, linear search runs in O of n, honest, simple, works on anything, slow on huge inputs. Idea 4, binary search runs on O of log n, lightning fast, but the array must be sorted and off by 1. Bugs love this algorithm. Trace it by hand whenever you're stuck, right? So yeah, I know what I said doesn't necessarily match up completely on the screen because this was meant to be like a question thing for the class, but I want to just give those 4 key takeaways that I have so far because I'm trying to focus on a final recap. And I'm just recapping all past 4 episodes, so that's why I revealed the answers instantly. I don't want to ask this anymore. I'd rather you guys listen to my recap and understand everything. That arrays are numbered boxes, Big O is a language for growth, linear search runs in O of n, and binary search runs in O of log n. Alright? So, yun. If you have any questions, feel free to ask it inside of the forum in my YouTube channel or comments. Anything that didn't click, I'd rather we fix it now than have you go home confused. So do message me on GChat or message me in my email and such, and I'm willing to help you out and provide learning materials. Alright. I think eventually, if you do want to advance study, I advise looking up stuff like linked lists, hash maps, and sorting. You want to check many different sorting algorithms as that's going to be covered eventually in future data structure classes. But the principles you learned today carry over, so please master all 4 of these principles in order to understand them. So you need memory layout, Big O, divide and conquer. Those ideas are going to be everywhere in the future. And if you're still confused in Big O, it takes a few sittings to click. Rewatch the growth chart slider when you go like reassess this whole video and play with the doubling demo on slide, I believe that's 20, right? Yeah, check the Big O video. These visualizations will do half the teaching for you. And yeah, I think next class we might focus on linked lists. So when arrays aren't enough, we meet a new data structure, the linked list. So see you then. Great work today, and thank you for listening to my lecture.